Hello and welcome back to Cracking the Cryptic. As usual, at the weekends we try and take a look at the Diabolical Sudoku, which appears in the Daily Telegraph newspaper on Friday. So without further ado, let's have a look at it. This is the starting grid here. Okay, so we can see simple Sudoku rules. Let us place a 9 here and 6 here. And what we'll do is we'll go through the solve, and I'll make pencil marks like this in 3x3 blocks, where a number can go in exactly 2 positions in the 3x3 block, and we'll see how far that takes us. Now, with these diabolical puzzles, it's often not enough, and so we often need to go beyond this at some stage in the solve, but we'll see how far we get. So you can see 2, 5, 8 down here and a 2, 5 here, so we can place a big 8 there and a 5 and a 2. It's a remarkable start for one of these puzzles. Normally, in fact, we can place another 2 there. Normally they give up their secrets only after beating us up a bit. So 2, 3, 7 to place in column 9. You can see there's sort of a dearth of 2s, 3s and 7s in the open positions there, so we can't really do anything with that. Let's go back to working on these central 3x3 blocks, I think. So middle block needs a 1, 3, 8, 9. We can place 8s there, place 9s here, and we can place 3s like that, I think. 8s there, twos like that, pencil mark some 4s into those 2 positions, some 5s into these 2 positions. No doubt most of you are noticing there's nothing clever about what one's doing at this stage of the solve. What we're really doing is trying to allow our mind the time to notice some of the patterns that are going on. I find this very difficult when I'm solving live like this, to actually record as much as I'd like to, but I think in that sense one of the worries with Sudoku solving is that it might not be good for your long-term memory and long-term concentration, because every new puzzle you do, you almost have to forget all of the patterns you just learned in the last puzzle. You can see in column 6, 7 here, we need a 1, 3, 4 and 7 to place, and this square here can only be a 7 because there's a 1, a 3 and a 4 already in row 1 there, which allows us to pencil mark some more 7s down there. 8s here, we can interact with the 8 here and here, and that gives us an 8 in this cell, and this is one of the advantages of using this notation. The moment I place an 8 in this cell, I can immediately place the 5, because I know that the 5 is going in one of 2 positions, so once this position is used up, it must go here. And you can see that's also going to give me it gives me the 8, 5 and the 4 instantly, and that also gives me this 4 because of the pencil marks up at the top of the grid there. And now the only challenge is to make sure that we use all of the information that we've just discovered. 5, 4, 3s now in one of those 2 positions, lock some 3s down there. And in fact we can lock, you can see this 1 and this 1 here. We're going to effectively get that pattern, but interacting with this 1 will allow us to place a 1 here and to place this 3. That's going to give us the 1, 2 and the 7 down there as well. Therefore this must be a 3. 2, 6 into these 2 positions, which isn't resolvable, I don't think, just yet. But now we just have to make sure that we use all of the stuff we just found. So first thing I can see is we can place 3s there, which gives us 3s into one of those two positions. So 5s there, look. 8, 7, 7. Oh, look, we can place a big 7 into that cell. 2 and 9 here, or 3 and 9, sorry, 3 and 9, so let's put that in. That gives us a 3-9 pair. You can see in column 4 here, this 3-9 here actually, it's not always the case using this notation that you can assume that where you have two numbers in a cell, they are the only two numbers that can go in the cell. But in this instance, you can see that we've actually pencil marked all 4 numbers here. We've got a 1, a 3, an 8 and a 9 pencil marked. So where that is the case, where all of the sort of unknown numbers have been pencil marked, this cell is effectively a double. So we have a 3-9, 3-9 here, which means that this is a 6-8 pair up at the top. Now that might be useful, and you can see now we have 2, 5, 7 and a 9 to place. So we can now pencil mark 9s there and there. And also 2, there's a 5. Can we do anything with 5s? No, we can do things with 7s, but not 5s. 7. 2, 3, 7, 9. 2, 3, 7. 1, 3, 6 here. So 1, 6. 3. Yeah, so we might be reaching the point now where we need to start using our brains a bit more. Oh, hang on a minute. Pencil mark 1s. This one here. Maybe that'll help us. 1's there. Yeah, okay. Now, what's okay? So just to stop me gabbling on while I try and stare at this, what I'm trying to spot now is, as usual, once we get to this sort of impasse with a very difficult puzzle, the pencil marks have taken us this far, and what I'm now trying to locate is cells in the grid that can only be exactly 2 numbers. And you can see that there are a number of these cells. So if we look at the middle row, for example, we're looking to place 1, 3 and 9. We have a 9 here. So this cell here, can only be a 1 or a 3. Now, using the pencil mark notation I've been using, if I was to place the 3 here, that would imply the 3 could only go in 2 positions in this 3 by 3 block, whereas actually it can go in 3 positions. Oops, go in 3 positions. So I have to remember, if I start to focus on this sort of square, you know, which squares I'm sort of mucking around with the notation on it. But in terms of weak cells, I'm thinking that there is an arrangement here with the bottom cell, the bottom row of the grid, because you can see in the bottom row we need to place 1, 3, 6 in the bottom row. This cell is also very restricted. It can only be a 1 or a 6, so let's highlight that. And this cell can only be a 3 or a 6. Now, last week I talked about Y-wings and the possibility of spotting Y-wings, and I described a Y-wing as being like a bent triple, and that makes them normally relatively easy to spot. So what do I mean by a triple? Well, a triple is exactly what we have across the middle line here. So let's imagine that this 8 wasn't there. I don't know if it'll let me delete it. It does. It lets me delete it. So you can see that we have a 1, 3 in this cell, a 3, 9 in this cell, and a 1, 9 in this cell. So we know that in working out what the empty cell can be, I would be able to eliminate the numbers 1, 3, and 9, because although I don't know where the 1, 3, and 9 go, I know that they will fill these 3 spaces somehow, precisely. Now that's very obvious when the numbers are in a line like this. And with a Y-wing, you normally have a small offset in this pattern. So it's like a bent situation. So it's still a triple, but it's bent. Now here we actually do have a Y-wing, I think, but it's very bent. It's actually bent at a right angle. So I'll add some highlighting after the video. But if we look at this cell and this cell and this cell, you can see they form a triple on the numbers 1, 3, and 6. Now that should, whenever you spot something like that, alarm bells need to be ringing. You should be asking yourself, okay, well, if there are these bent triple situations, we need to be testing what happens when we muck about with the middle cell of the triple. So this one, this 3, 6, you can see, probably many of you are already there, but whichever number I selected to go in this cell, which is normally called a pivot, I think, in the technical sense, that has an effect. It has the same effect on this cell and this cell, i.e. if I pick this cell to be a 3, this cell is forced to be a 1, and if I do the opposite, if I pick this cell to be a 6, this cell becomes a 1. And what does that mean? Well, that means that any cell in the grid that can see both this cell and this cell cannot contain a 1, because no matter what we pick for this, there are only 2 options, yeah, either this cell or this cell will eliminate 1s in cells that these 2 cells can see. Now which cells can both this number and this number see? Well, unusually I think it's just the one cell. It's this cell. Both this cell and this cell see this cell, so there is no way this cell can contain a 1. And let's just prove that to ourselves by, we'll just make it a 1 for the sake of argument, just to illustrate the problem. If this is a 1, this cell's going to be a 3, this cell's going to be a 6, and now there is no way to fill this cell here. We can only put a 3 and a 6 in it, and neither can now be placed. So let's, oh goodness me, now I'm making a right mess. Delete that. Okay, so it's allowing me to delete things now, so that's good. Right, so what do we need to do? Well, we know we can remove the 1 here. That forces this to be a 9. Now, once this is a 9, this is a 3, this is an 8, and this is a 1, just because of the way the pencil marks unwind here. This, therefore, has to be a 1, and this has to be an 8. Now, I can't remember what this was when I deleted it, 2 by the looks of things. So let's get rid of that. Okay, and what are we left with over here? 3 and a 7, which, oops, 3 and a 7, like so. Now, what I should probably do is remember some of these pencil marks that I've put in, so I'm actually going to remove them now because they're going to confuse me otherwise. Okay, you can see that this 3 here interacts on this 3-9 pair, so we can unwind that like that, and that's going to be very useful at the top of the grid. And now this has to be a 9, which means as well this has to be a 7, which allows us to pencil mark some 7s over there, look. This cell here can now only be a 5, and we're left with having to place the numbers 1 and 6 into these 2 cells, which I don't think we can resolve yet. 6, so that can't be a 9. This is 2, 5 pair there. I keep looking for some uniqueness opportunities, but annoyingly the 2 and the 6 here are already rendering the uniqueness opportunities over in column 2 sort of superficial. Has that number disappeared? to replace the pencil mark 3 that we had down there. Okay. Again, we're sort of back in grid staring mode now. I mean, one thing to note is in any sort of competition scenario, a pair of 8s there, maybe that's useful, you'd be far quicker guessing at this stage. Just switch to pencil and eraser and see if you can force out an answer. I don't really want to do that, so I will just stare at this for a bit longer and see if I can see anything clever. No, still not seeing anything particularly good. So I think in order to really nail this down, I'm going to have to fill in the candidates for the remaining cells. I really hate doing this, but I can't see how to make more progress mentally here. So let's just quickly do that. So 1, 2, 6, 9, 2, 6. That's interesting. 1, 2, 6, 9 there. 3, 7, 3, 7. Okay, so 2, 3, 6, 7, 9. 6, 9 there. 2, 6, 7, 2, 6, 7. I think this cell here. Yeah, so there is quite a lot of restriction now actually. Oh, I haven't done this one. So 2, 3, 5 and 6. So you can see that's got to be a 2, 3 or a 6, I think. Okay, so we can't do quite the same thing as the Y-wing here, but we can use the same sort of principle. So all I'm doing here, to be honest, is I'm testing numbers in some of these cells that only have 2 possibilities, and I'm seeing the effect of that as I trail around the grid. And you can see that because we have so many digits or squares in the grid now that can only contain exactly 2 numbers, there are a lot of forced chains. So if we look at this position, for example, this could be a 6 or it could be an 8. But if it's an 8, what happens? Well, if this is an 8, this is a 9, yeah? This is a 1, this is a 3, and this is a 6, therefore. So again, we have this sort of limiting thing whereby either this is a 6 or this is a 6. Now what that means is I'm looking now for numbers or squares that both this square and this square are pointing at. You can see this square, for example. This square can no longer contain 6. So let's remove that 6 and see what that means. And now surely. Okay, yes. Now this square we can do the same thing with. This square can be a 2 or a 5. Okay, so if this square is a 2, that's fine. If this square is a 5, you go off on one of these forcing chains again, because watch what happens. If this is a 5, this is an 8, this is a 9, and this is a 2. Okay, so either this is a 2 or this is a 2. So now we need to be looking for cells that see both this square and this square. Now this time there are a lot more squares. There are 3 squares that see both this square, and we can eliminate 2 as an option in those 2 squares as a result of that forcing logic. And now it looks like that cracks the puzzle. I mean, when you get to these very late stages, any sort of deduction like that is going to be very powerful. You can now see we have a 6-7 pair in row 2. That's going to allow us to place an 8 here, and a 6 here, a 6 here, and a 2 here. And I think this is this must be done now, isn't it? So that's going to be 9, 8, 5, 3, 1, 9, like that. Then this cell is going to have to be a 2, which makes that a 6. So it's going to be a 2 now. 6, 1, 3, 7, 3, 7, 6, 2, and 5. So there we go. So a couple of interesting things there. I think the Y-wing was instructive and spottable, you know, without going to terribly great lengths. I have no idea what you call the other things we found, but it's the same sort of principle. But for that, unusually, I actually needed to write in all possibilities for the open cells, which I really, you know, in a speed solving contest, you can never do that. In a sort of logic problem scenario like one of these videos where we're trying to show logically how to make further progress, we can do that, but in fact I think this is the first video where we've needed to. It could well be that I've missed something. I know that some people like to use online solvers, and so if there was a clever, more elegant way, please do let us know in the comments, and perhaps I'll do a follow-up video to explain how that would have worked. But this time we needed to use all the possibilities and sort it out that way. So thanks for watching, and we'll be back soon with another edition of Cracking the Cryptic.